Hi, everyone. Welcome to the weekly C3.ai Digital Transformation Institute Colloquium series. I'm R. Srikanth. I'm one of the two co-directors of the Institute. So the DTI is a consortium whose aim is to promote the use of artificial intelligence, machine learning, IoT, and cloud computing for the betterment of society. We are a consortium of many universities. They're listed here, and two national labs, the Lawrence Berkeley National Lab and the National Center for Supercomputing Applications. And we are funded by C3.ai with computing support from Microsoft. Before I introduce today's speaker, I want to mention that there's one more seminar or colloquium this semester, and then we'll resume in the spring. Our final colloquium for this semester will be given jointly by Karen Chappell, Tim Thomas, and Peter Hepburn. It's on housing precarity, eviction, and inequality in the wake of COVID-19. And it's next week on December 10th. I guess I want to give you one more piece of information. There is a workshop on Monday and Tuesday, and it's on a very hot topic on the how to make autonomous systems safe. And it's jointly organized by Gare Delarue at Illinois and Claire Tomlin at Berkeley. And it'll feature an all-star cast of speakers from both academia and industry, companies such as SpaceX and government institutions such as the National Science Foundation. So it'll be an exciting 2 days. And if you have the time, please feel free to join us. And I think there's a link to the workshop page on chat. You can click on it to find out more information. Attending the workshop is free, and it starts at 9 a.m. Pacific time, 11 a.m. Central time on Monday and Tuesday. Regarding the format of today's colloquium, it'll be roughly a 40-minute presentation, but I think the speaker today has said that he will pause every now and then to entertain questions. So if you have questions, please post them on the Q&A box, and I'll ask them to the speaker. So roughly 40-minute presentation, maybe the overall question and answer session time will be 15 minutes. And you are welcome to upvote a question, and if a question receives many upvotes, it'll of course move to the top, and I'll ask those questions first. We'll try to get to as many of the questions as possible as time permits. So today's talk is on stochastic optimization of inventory at large-scale supply chains. And we have an outstanding speaker today. Is Dr. Mehdi Maasoumy. He's a principal data scientist at C3.ai, and he leads teams that use machine learning, deep learning, and optimization algorithms to use AI to solve previously unsolvable business problems. And as many of you know, stochastic inventory optimization problems for supply chain and predictive maintenance can be very, very difficult. And he leads a team that provides solutions to a variety of industries, including oil and gas, manufacturing, energy, and healthcare. Mehdi holds a MS and a PhD from Berkeley and a bachelor's from Sharif University of Technology, and he's a winner of several Best Paper Awards. Mehdi, you can take it over.
Right, thank you very much, Srikanth. Very happy to be talking about this problem today and going over this subject with you all. Before delving into the presentation, I would like to thank and acknowledge the great work of a lot of people who have contributed to this work. This has been a true team effort by data scientists in C3 side, as well as a lot of collaboration and guidance from our customers over the years. So thank them for their support and the help that they've extended to us in defining this problem space, refining it with us, and helping us mature the product. So with that, let's get started. As we stand today in late 2020, there's a general consensus that the world is going to be very different post-pandemic era. And that is mainly driven by two factors. One is the supply shock that we experienced in China back in February. The consequence to that, to the pandemic, the global and widespread demand shock that was essentially absorbed to the system and by the system in the ensuing month of 2020, that has essentially exposed the vulnerabilities in the supply chain and has led the leaders in the manufacturing space and supply chain space and companies in this space to rethink their strategy, and start to re-strategize and adopt lean manufacturing strategies and processes. And as a result, essentially adopt policies to minimize the amount of inventory that they hold on global supply chains. So let's look at this problem. We basically took this as a challenge and looked at the whole problem space of manufacturing and supply chain, and identified areas of common issues as it relates to supplier side, transportation, all the way to customer side. There are issues such as order delays and quantity uncertainty on the supplier side. Lack of visibility.
Sorry to interrupt. We're not seeing your slides. Are you sharing your screen?
Yeah, I should be sharing. Let me do it one more time. Okay, how about now?
Looks great, yes.
Okay.
Thank you.
Thanks for pointing that out. All right. So as a result of that, we started looking at this problem space and identified common issues. In supplier side, we notice order delays and quantity uncertainty problems. In transportation, there's a lack of visibility and arrival uncertainty. In manufacturing process itself, we see problems such as quality and yield issues, and in the distribution and customer side, problems such as transit delays and on-time in full uncertainty and dynamic demand. And taking into account the fact that the network aspect of this problem essentially makes any issue or any event in this whole supply chain to propagate and cascade through the whole network. We see phenomena such as when dynamic demand and order changes, it impacts the production schedules and the inventory management in the manufacturing sites. And that in part, when there's inventory and production requirements change, that informs supplier orders. On the other hand, supplier uncertainties and delays can affect production schedules, where in part the order delays and quality issues can risk customer satisfaction. So as you look at this general value chain, you can notice a lack of end-to-end operational visibility that is apparent, as we don't have all the data in one unified common data image that can help us get a better sense of what is going on and try to optimize the process, which can lead to delays across supply chain. It can lead to excess inventory levels, quality issues, poor on time in full, and low customer satisfaction. So this looks like a very daunting problem. We took it as a challenge, and we basically came up with several solutions that spans across the whole supply chain problem space. Problems such as, or solutions rather, such as supply network optimization, yield optimization, and predictive maintenance are common solutions to solve these problems. And today I will only focus on one of these, being the inventory optimization problem, and I'll go over what we have done in this space. So what is the problem statement in a nutshell? The idea is to minimize inventory levels by recommending optimal set of order parameters subject to a predefined service level requirement. That's essentially what we're trying to do. The objective function is a cost associated with holding inventory, order cost, and lost revenue, subject to some operational constraints such as planning calendar, planning time fence, other time-based constraints such as lead time and expedited lead time that have to be respected, time varying characteristics on the supply and demand side, and last but not least, service level requirement, which is defined as the probability of not hitting a stock out or not running out of parts during the replenishment cycle. So this is the optimization problem or the problem statement that we are trying to solve. But before delving into the solution, let's look at how the supply chains are managed today. So as we stand today, the centerpiece of the supply chain management system is the material requirement planning that are used generally by majority of manufacturing companies. The MRP, in short, takes as input demand forecast for each item, current day inventory, planning calendars, order parameters such as minimum order quantity and rounding value, planning horizon, and also previously scheduled arrivals. And it comes up with a set of scheduled arrivals over planning horizon. And MRP does so by respecting certain time constraints, which you can see in the bottom of the page. As an example, it is too late to schedule any arrival to arrive before expedited lead time, while arrivals or arrivals scheduled to arrive between expedited lead time and lead time are considered to be expedited arrivals, which, by the way, they cost more and are more limited. And any order which is supposed to arrive after lead time is considered a standard arrival. On the other hand, there is a concept of planning time fence, which means previous orders that are scheduled to arrive within planning time fence are locked and cannot be canceled. So MRP basically takes these time constraints into account and places an order when given the demand forecast and the rest of the input. For an illustration, let's walk through this example. So let's say the requirements in the future for a given part is 50. And we have already on hand 45 of that specific item. With a safety stock of 5, the MRP calculates that we need another 10 parts because we need to keep a safety stock of 5 at all points in time. Therefore, simple algebra gives us quantity of 10. This is in a nutshell what MRP does, but a bit more complicated than that. Let's go over some of the input data to MRP, which helps the MRP place orders and do what it does. One of the most important inputs is the bill of material, or BOM in short, which is essentially the list of materials, components, and subassemblies which are required to make a end product. The end product itself is sometimes called independent demand or level 0 on BOM. There is also quantity and the time that the quantity is to be arrived or required input to the MRP, as well as current inventory and some planning data, such as economic order quantity, scrap percentage, and so on, which are input to MRP. The concept of delay is very important when we have products that are that have multiple levels of purchase part and components. When in this case, for example, purchase part 3, as an example, is delayed, in part it delays the production of component 2 and further delays the production of the top level product. So we need to take into account this cascading of delays and the resulting trapment of entrapment of parts, which will essentially increase the inventory holding cost for other purchase parts. So these are all the considerations we have to take into account. And by the way, on these slides, I'm going through a lot of nomenclature. This is meant a bit of educational to bring up to speed the audience on the terminology and also the requirements and the problem space, to introduce the problem space a bit more. So bear with me and I'll jump into the solution in the next couple of slides. There's a concept of demand, dependent demand and independent demand. Independent demand is demand for the end product. Let's say if you're making a computer or a bicycle, that is the independent demand. And dependent demand is defined to be the components or parts or assembly or sub-assemblies that are required to make that final product. In the case of computer, it could be the microchips, and in the case of bicycle, it could be the wheels. And quantities for this dependent demand are derived from independent demand using the BOM. And MRP basically takes care of that and breaks down the BOM and derives the independent demand. It also takes into account the lead time, because each of these parts could have a different lead time. And if one of them has a larger lead time, MRP has to place the order earlier such that they all arrive at the same time. So if we take that problem and cast it as an optimization problem, this is how it's going to look like. We are minimizing the inventory holding cost plus order costs and lost revenue, subject to the probability of running out of inventory being less than a given threshold, and additional operational constraints. And these operational constraints include inventory balance equation, the minimum order quantity, rounding value constraints that have to be respected, planning calendars, and so on. And the idea is that we would like to leverage the inherent uncertainties in both supply and demand side to find the optimal set of parameters to optimize this cost function. So that's essentially the merit of this optimization problem. So let's see how the cost function and the constraints look like. In the cost function, we have C sub O, the ordering cost times the arrivals, plus C sub S being the storage cost times the current inventory level, subject to essentially the mass balance equation that gives us the number of available inventory at any point in time for any part K as a function of its initial inventory plus its arrivals minus the demand. We also have additional constraints on the inventory itself that has to be greater than or equal to 0 at all times, and the arrivals also have to be non-negative. Using the big M method here, we incorporate the concept of minimum order quantity and rounding values into the formulation. So here you have those minimum order quantity and rounding values, which are specific per part K, integrated into the formulation. And as a result of that, we get the problem. The next step is obviously the uncertainties that we see in the world. No, we're not living in a perfect world, and there are uncertainties associated with different parts of this problem. The main sources of uncertainty that we consider here are supply uncertainty on the time and quantity axes, the uncertainty associated with demand forecast, and the uncertainty with respect to material movement. In the next slide, I will define what these are and what we mean by these. But this is essentially where the source of uncertainty gets into the optimization formulation. So the total uncertainty is a function of demand forecast uncertainty, which itself is the difference between demand forecast and the actual demand, or rather actual consumption. Material movement uncertainty is the sum of miscellaneous and block material movement, and supplier quantity uncertainty is the difference between order quantity sent to the supplier and the total quantity received associated with the same purchase order. And there's also auxiliary uncertainties, which could be customized per customer's operations. We use the supplier quantity uncertainty to essentially sample from this its distribution, and use it in the simulations later on. I'll talk about that later. And on the time axis, the way we model time uncertainty is as follows. Time uncertainty is essentially the supplier time delay. And the time delay is estimated by the difference of the delivery date, which is specified on the contract, and the actual final delivery date of the same purchase order. This could get tricky because orders get modified over time, and the delivery date on the contract, the initial delivery date might change over time. So we have to take care of that and make sure that we are taking the right date, which is typically customized by discussions with the customers. But at the end of the day, the time uncertainty is used for sampling the time delay, and we use that as a supplier quantity uncertainty. This arrival date will be adjusted based on the sample of from the empirical distribution that we get from this time uncertainty, and we apply it in the solution, as I'll go over later. So the way typically uncertainties are dealt with in optimization problems is through buffers. And here is exactly what we do. We consider a quantity and time buffers. These are standard ways of handling this problem. Safety stock is a quantity buffer, which is related to additional inventory that has to be held in order to respect the quantity uncertainties that we will experience. So as a result, the constraint on the inventory level will be xk greater than safety stock, as opposed to xk greater than or equal to 0. And safety time, similarly, is a time buffer related to when or how long in advance we should place an order or schedule arrivals to provide robustness with respect to the delays that we will experience later on. So as you can guess, the MRP that we have discussed so far can be expressed as an optimal control problem. Essentially, we have an optimal control problem that we can solve using dynamic programming. But historically, in the commercial solutions that you can find out there, this solution to the optimal control problem was perceived to be too complex. And as a result, there were several heuristics developed in order to simplify the problem and the solution to the problem, which in part make gross simplification and simplifying assumptions. For example, there is this silver mill heuristic where essentially boils down the problem into finding the average cost per period as a function of number of periods that the current order spans, and stopping the computation when this function increases first. There are other well-known methods to find the order quantities. Dynamic lot sizing was developed back in the 1958, and the corresponding heuristic to that was developed in 1973. As you might imagine, as a result of some such simplifying assumptions and heuristics, the solution to the MRP that is out there today in the market is not going to be optimal. And to delve into the MRP logic a bit more, this is what it looks like today. We have inputs of safety stock, safety time, demand forecast, and such. And we have to respect those time guardrails as I described earlier. And the solution to the MRP can be summarized by this algorithm, which is essentially by running some algebraic calculations on the inventory levels, we come up with arrivals and schedule and scheduled orders. We believe that there are at least 3 major drawbacks and issues with the way that the classic MRP is solved. And these issues are as follows. As we already covered, the solution to the simplified MRP does not guarantee optimality because of those simplifying assumptions. Secondly, the MRP relies on input parameters such as safety time and safety stock, which are currently set by the end user in an ad hoc fashion and without rigorous analysis of uncertainties associated with the historical data. And thirdly, the approximate solution to the MRP does not learn nor adapt to the uncertainties that are time varying and customer or supplier dependent that surround the manufacturing process. So these are 3 main reasons as why MRP and its classical solution, the classical solution to the MRP is not enough, and we can do better. So let's now look at what we have done to reformulate and resolve this problem. So we're essentially going from a world in which there are disparate siloed data sources across multiple ERP systems. There's a lack of end-to-end visibility into the supply chain. There is overly conservative inventory estimates and no ability to simulate changes to MRP, into a world where we have a unified data image of all data across the enterprise, which leads to reducing inventory costs and improving service level, and providing a visualization capability on top of that with an end-to-end scenario modeling, and also an evidence package or interpretability logic that explains why we made a certain recommendation alongside with actionable insights to the end user. So that's the vision, and that's the product we have built. So why hasn't anybody done this in the past, or why hasn't this been adopted in the past? There are 2 main reasons. One is computational challenges associated with solving this problem at scale. And the other one is the inability to unify and process data across time and space at the enterprise level. So these are the 2 main reasons why the adoption of the true solution to MRP has been impractical in the past. And today, thanks to the power of modern elastic compute, these problems can be overcome. And the original MRP optimization problem can be solved with proper treatment of uncertainty. And that's in fact what we have done. The C3 AI inventory optimization essentially reformulates and solves the supply chain and inventory problem as a constraint stochastic optimization problem. So before I move further on, I would like to pause and see if there's any questions. I don't know if there's anything in the chat. I can't see, but
I don't know if you will answer this maybe later on, but can you tell us what sort of dimensionality you're dealing with? What is the time horizon? What is the number of variables you typically deal with, and so on?
Yes, good question. And yeah, let me get to that when I talk about the solution in next few slides.
Okay, we'll wait on that then. There's a question on the Q&A box which says, how does the solution compare to the Graves-Willems approach of solving the inventory optimization problem? Although that's for deterministic case, I guess.
That's right, yeah. So we have to consider the uncertainties, and that's the reality of the real world we are living in, and our customers are living in. As a result, there's not a one fair comparison between the 2, but I'll at the end of this slides I have some results that I will explain how the performance of this solution and technique is, and I'll walk you through some examples.
Thank you.
Awesome. All right, so let's move on. The idea is that we are going to now reformulate and solve the problem of MRP in a true optimal fashion. However, it was not that easy because we couldn't really start from scratch. We had to work with the legacy infrastructure and legacy systems that are deployed across customer bases, being the MRP. So today, as I mentioned already, there's an MRP and there are inputs and outputs to the MRP. And some of the inputs to the MRP are the order parameters, such as safety stock and safety time. And in order to comply with this existing legacy infrastructure, we decided that we will keep the MRP for now, and we will only essentially come up with an optimal values for safety stock and safety time, and we replan and re-optimize them as we go. So that's essentially the framework. And so in the past, basically this decision had to be made by the material planner, which would make a decision pretty much based on experience and without rigorous analysis of the true case of uncertainty and true distribution of uncertainty, which we are essentially eliminating that, and we are devising this optimization problem that would in part make a decision instead of the user, instead of the human. And we recommend the optimal safety stock and safety time instead of the user. In addition to that, we are also adopting this receding horizon optimization framework in which we are going from a paradigm that has to do with very infrequent changes to safety stock, and typically changes that are not very well studied, or changes that are not rigorously examined, and a space in which once coming up with this solution with this safety stock, you don't have a view of what your inventory is going to look like, to a new paradigm in which we propose or recommend optimal safety stocks, and we can update them at a timely manner with enough visibility into what the effect of these recommendations would be on the inventory level, and the uncertainty associated with that. So this is essentially where we're going with this approach. This is the high-level view of the algorithm. It's composed of main two aspects. The first one being a training or offline phase in which the optimization happens. We find the best combination of service level percentile and safety time percentile by running this optimization and running MRP, numerous runs of MRP, and realization of uncertainty that we have learned from historical data and the quantile models that we have trained on those uncertainties. And we do that offline because mainly this is the more expensive part of this process, the optimization part, given that each MRP run is extremely expensive and extremely time consuming. We have to run lots and lots of MRP runs, so that part is usually done offline. And there is an online phase or runtime phase where we take the best service level percentile and safety time percentile that we have found in the optimization time, and we determine the corresponding safety stock value and safety time value with one and basically run one step of MRP. We apply uncertainty realizations to that n number of times in order to get a full picture of what the future inventory would look like. Then the inventory MRP run is run to get the simulated inventory, and we repeat this process for t times in the future. And as a result of that, we compute the inventory cost and the service level and the service level associated with that. So essentially, it's done in two phases, as you can see. To answer one of the questions that was asked earlier in terms of size of the horizon and the windows, these are typically configurable. We have worked with training times being at least 1 year up to several years of data, and the test or online phase being several months as a typical example. And the horizon that we take into account has to be more than planning time fence. So those are essentially the indicators for us on how to pick the horizon values. It's part dependent, and it depends on the planning time fence and lead time associated to that specific part. So there are main two parameters that we're optimizing here. The first one being the service level percentile. The service level percentile essentially describes the trade-off between how conservative or aggressive the choice of safety stock value will be. Obviously, high service level percentile, let's say 100, would put the entire uncertainty simulation above 0, while a lower service level percentile, in this case, if you consider a 50% service level percentile, would put the median curve only the median curve above 0. And here the trade-off is between a low service level percentile being more aggressive strategy, which would lead to a much lower inventory cost and much higher risk of running out of stock, versus a high service level percentile being the reverse. And as you can see, this is one of the tuning parameters that we have that we optimize over. The next tuning parameters is the safety time percentile. Essentially, the safety time percentile helps the algorithm pick the right safety time. As we're living in an imperfect world, supplier delay is always expected, and that can lead to stock out if you have enough delays on your supply side. And the idea is that we learn this distribution of delay from the training period, and we use this safety time to place all the orders earlier. So we shift back all the orders that we would have placed otherwise. And with the expected delay, when the expected delay happens, the actual arrivals is guaranteed in some sense or with some probability to be not arrive later than the expected arrivals. And these examples, in this toy example, on the right, you can see the supplier delay in number of days. So, in this case, for example, the 100 percentile would be 6 days of delay, and the 50 percentile would be 3 days of delay. The question is, which one do we pick now when it comes to the optimization problem? Do we go with the extreme case? Do we go with the 50%? And how do we optimize over this? The idea is that, again, there is a trade-off where safety time percentile decides how conservative or aggressive the safety time is, and a low safety time percentile of, let's say, 50% would 50 percentile would place orders 3 days earlier to account for the 50th percentile of delays, while the higher safety time percentile would place orders 6 days earlier. And these are, again, another tuning knob for us where a low safety time percentile would lead to a high risk and high return, while a high safety time would lead otherwise. So with these two in mind, we define in the next step an objective function. The objective function can be customized. It could be the median inventory cost, or it could be the median service level, or it could be a combination of the two, whichever fits best the operation of the customer. We define that objective function, and we search in the space of service level percentile and safety time percentile to find the best combination that gives us essentially the minimum objective function. In this case, let's say if you look at the top right plot, we have found the best combination to be A and B. We take that, having learned those A and B from the training period, and we apply it on the test period to the data. At each time step, we replan and re-optimize for that. Putting these two together, the algorithm, the offline and online phase of the algorithm is as follows. So you have a training period, which is done offline. You look for the optimal set of service level percentile and safety time percentiles that would satisfy your constraint and would lead to minimum cost function. And in the test time, at each time t, there's a mapping between service level percentile and safety time percentile to safety stock value and safety time. We take that, and those will be essentially the optimal parameters input to the MRP. And as you remember, we're still using the MRP as part of the plant in this problem, and we are only optimizing around the plant. So in this case, once we define the optimal safety stock value and the safety time value, we run one MRP simulation with multiple uncertainty realizations, where those uncertainty realizations are observed from or are sampled from the empirical distribution that we have learned in the trained phase. And we simulate the inventory further into the future, which is meant to be a lightweight simulation as opposed to the heavyweight simulation of the training phase. So as you notice, one of the characteristics of this approach is that it provides a more robust optimization results. If you think about it, the actual delay or the actual quantity uncertainty that you experience in real life is indeed one realization of all the possible delays or supply quantity uncertainty that you could have experienced. And in order to be robust against a class of uncertainties associated with supply quantity and time, we run multiple realizations, or we sample multiple realizations of the uncertainty, and we make sure that we define the cost function and the constraint in a way that for X percentile of those realizations, we're always going to be safe, and that's how the constraint on service level is enforced. In this case, for example, you can see that if we take the 50th percentile on supplier quantity, blocked and material movement, it leads to minimum inventory level while satisfying the service level constraints. And there's always a trade-off between a high cost and high service level. In this case, we have on the top a very high inventory cost with a good service level, but we are keeping too much inventory. While in the bottom plot, we see a much lower inventory cost, but the service level has taken a big hit. And none of these are ideal, and we are trying to strike the right balance between the inventory cost and service level via this approach. going a bit more into the details of the two phases, I'll quickly go through this. We essentially during the train phase for each hyperparameter per service level percentile and service time percentile, and for each time t, we learn the empirical distributions of demand, quantity, time, and material movement uncertainties. We determine the safety stock value and safety time with that given pair, and we run the MRP we sample from the uncertainty distributions, and we get the simulated inventory, and we evaluate that the cost and service level associated to that inventory and for the given period. And once we reach the minimum cost function value or loss function, we pick that service level percentile and service times percentile to be the optimal. And in the test phase, which is essentially happens in runtime, having computed those service level percentiles and safety time percentiles, we derive the right value for safety stock value and safety time value at every point in time, having realized the new state of the system and having access to an updated demand forecast and such to update the values of safety stock and safety time. There are some considerations with respect to how we pick the values for service level percentile. We have to realize that it is always expensive to remove all the risk. There are always outliers in the system, and if you want to be N9 robust against those uncertainties, it's going to cost a lot. So we are make sure that the solution is robust against those outliers, and in picking the right service level, we make sure that the search space is rich enough that would avoid getting stuck at one of these not very optimal solutions. And on the other hand, the safety time percentile gives us, again, the same. It's always expensive to remove all the risk, and if we want to optimize for the largest delay we have ever seen, it's going to, again, cost a lot because we're going to push back all the orders by too long, and we're going to end up with a lot of inventory on hand. So with that, I'm going to walk through results very quickly and then open up for questions. We have applied this methodology and this approach to various use cases and problem spaces, from HVAC equipments like chillers to agricultural machinery, construction machinery, to discrete manufacturing. We have applied this to auto part manufacturing, medical equipment, as well as measurement and sensing systems. And the results are as follows. I'll just show a few examples and some high-level description of the results. In this case, as you can see, there's a part with high inventory reduction, where the algorithm recognizes that this part has low uncertainty associated with it on the supply and demand, and hence it doesn't place any orders and allows the inventory to drain, while the original MRP kept placing orders and essentially shoot up the inventory to very high values. We've reached 52% inventory on this part, for example. There's another part where the algorithm accounts for orders that are already placed, but reduces the inventory level by avoiding placement of additional orders. And as you can see, after some time, we realize reduction in inventory. In this case, we see that the algorithm considers the variability from supply facility, and it essentially leverages that variability on the supplier side to adjust the timing of the orders. And by adjusting the timing of orders, we reach a certain level of inventory reduction. Similar examples here. We have algorithms that account for orders that are already placed, but we end up reducing inventory by avoiding additional orders. And in this case, we leverage the case where we have to respect the service level constraint of more than 90%. So we barely meet that, which is enough, but we end up reducing inventory by a few $1 million. And in this case, these are all different use cases that I mentioned earlier. In this case, we are reducing inventory by about 30%. And at the same time, we are improving service level from 85 to 98% and from 80 to 96% for different reordering parameters. This is the summary of the results and a little bit of future work before I open up to questions. One of the areas that we are working on, given the expensive run of MRP for each realization of uncertainty, we are looking into using deep learning models to learn from vast amounts of data and find essentially a representative deep learning model that mimics the MRP and use that to more quickly simulate the inventory over time. The other area of future work that we are currently working on is multi-echelon optimization, where the idea is to optimize inventory across multiple facilities and multiple distribution centers. One of the other areas is to make sure that the optimization solution is robust against such parameters, such as some parameters such as initial inventory, and it marginalizes the effect of those away on the recommendation of the safety stock and safety time. This is one of the feedback that we've got from customers, and we have a solution that basically does this on this side. And the ability to perform regime shift analysis and detect when retraining is needed, because currently we have some cron-based retraining of the models, while a more efficient way of doing so would be to have a regime shift analysis to detect when there is a shift in supplier behavior or demand behavior or the whole system end-to-end before and essentially trigger a model retraining before making new recommendations. So with that, I would like to open for questions. Apologies, I think I'm 5 minutes over time, but happy to take questions.
Thank you. That was a wonderful talk. It's a nice combination of theory and practice. So there are a couple of questions in the Q&A. So one of the classic real-world challenges, I think this is a question from Srinath Chidambaram. One of the classic real-world challenges is when suppliers get delayed due to capacity constraints. Most solutions interpret that delay as additional buffer requirements, which only makes the supplier's delay worse due to more requirements on them. How does your optimization handle this dilemma? In other words, is it right to assume supplier uncertainty as independent of orders placed? I guess the question is, are you assuming the supplier uncertainty is independent of the orders placed, or are you taking into account the dependence?
Very good question. So I'll answer it with in one direction. I'm happy to take it on further offline. But what we have realized is that there are two axes. One is time, and the other one is quantity. The uncertainties around these two axes are quite distinct, and having delay present in the system, it's very hard to accommodate for the delay using only safety stock and using quantity buffers, and vice versa. If you have only trying to accommodate for supplier uncertainty and quantity uncertainty using time buffers, it becomes very hard, and you end up with a suboptimal solution. That's why we, in the solution that I presented, there are two distinct axes, time and quantity, and each serve their own purpose and jointly lead to the right and optimal solution.
Thank you. So the next question is by Yang Kong. What's the current stage of optimization of inventories across multiple facilities and distribution centers?
Good question. And this is, in fact, one of my future work that I presented, the multi-echelon. We have done quite a bit in that direction, I have to say. One of the major challenges that we were facing early on when we took on this challenge was that the optimization problem would take, even for single echelon, would take a very long time. And because there was a huge computational cost in runtime, scaling that across multiple facilities would have proven to be difficult, if not impossible. One improvement that we have made is to essentially move a lot of the training into an offline period where we learn the right set of hyperparameters, the supplier, the service level on percentile, and the safety time percentile. And having that, we basically pick that and use that in ongoing analysis. This allows us to be able to run less MRP simulations, which speeds up the process, which enables us further down to be able to run this at a larger scale and across multiple facilities. And the other area we're working on is to basically show some proof of concept where we can say the same framework essentially enables us to solve the problem at a multi-echelon scale, and we are currently working on that, and hopefully I can present the results on the next series.
Okay.
Multi-echelon.
So I think there's one more question. We'll make this the final question because we're coming up to the top of the hour. So do you foresee using reinforcement learning in the multiple facilities and distribution optimization issue? I guess, yeah, this also, I had this question too, because I guess initially you mentioned that this is a dynamic programming problem. And then if you think about chess and Go and all these games where there's been much success using reinforcement learning, they're all dynamic programming problems. So do you see the use of reinforcement learning, especially deep reinforcement learning, using neural networks and reinforcement learning together?
Absolutely. Again, another good question. And yes, we have thought about that. One of the challenges we are facing with jumping into a reinforcement learning problem is data, and having enough data that would justify running this, or basically adopting a reinforcement learning solution. We do have enough data from, let's say, one customer or one facility, but in order to get good results for reinforcement learning, we need a lot more. And we are looking into areas where we can combine data from multiple facilities of a customer, and also solutions such as data augmentation that would help us simulate more training data, having learned initial MRP behavior, such that we can then feed this to reinforcement learning. But yes, this is something that we've thought about. We have not. I can't say we have. We have the solution for it, but definitely on the roadmap.
Okay, thank you very much for that stimulating talk, and thanks to the audience too, and hope to see you all at next week's colloquium. Thank you. Bye.
Thank you.